In this video, we will learn about the manufacturing scheme of cement, that how the cement is manufactured in the industries, what are the schematic flow of the processes involved in manufacturing of cement. These are the flow diagram of this is the flow diagram of the cement manufacturing, starting from the query and ends at the dispatch. There are the several processes involved in the cement industry. First, we have to extract the raw materials at the query site. Then raw materials are crushed and grinded and homogenized into some specific particle size, and then the crushed materials and grinded materials are subjected to the preheating. The feed afterwards is subjected to the kiln for the at a higher temperature so that the clinker can be formed. This is basically a rotary kiln at which there are different temperature zones, so that the calcination of the products occur. Then then the clinker formation at a higher temperature around 1450 degrees Celsius is formed. Afterwards, the clinker is grinded into some finely grounded particles, so that the gypsum and other additives are added at this portion. Afterwards, it is forwarded for the packing and dispatching to the market. This is basically the querying and separation of constituent materials. As I have discussed earlier in previous video about the chemicals and different geological materials involved in manufacturing of cement, lime, calcareous and argillaceous rocks are used in manufacturing of cement as a prime constituents. So querying of the lime and argillaceous materials are carried out in first stage. We do the querying, but we do extract the materials by blasting at the query site or by some other mechanical means. So after the material in boulders are collected at query site, these materials are then transported to the cement production plant through some sort of a transport. Afterwards, these materials are separated. These materials are crushed into some specific particle size, so that it can be further processing in manufacturing plant of cement. The material which were crushed earlier was conveyed to the raw mill through a conveyor belt, and this raw material um, is used to grind into specific particle size of so that the maximum particle size, nominal maximum size particle size, should not exceed 90 microns. Then the preheating of the feed material is occurred, and in preheating, basically the constituents, either it's a limestone or some argillaceous rocks, are preheated at a high temperature around 7 to 800 or 900 degrees Celsius, so that it can gain, so that the calcination can occur and limestone can convert it into some quick lime, which is very reactive in nature as compared to the limestone. On the other hand, the calcareous, argillaceous rocks, argillaceous material which contain the silica, alumina, and iron content, is separated by means of a preheating. So after the preheating, the material is just forwarded to the kiln, rotary kiln, which is inclined at some angle, ensuring that the material passes through by the partial molten form. There is a fire source at one end of the rotary kiln. Near this fire source, the temperature is too high. When we go away from the fire source within the rotary kiln, the temperature is quite lower as compared to the nearer places. So after passing through the feed material into the rotary kiln, the out product is basically the clinker. The clinker contains the chemical composition in the form of tricalcium silicate, dicalcium silicate, tetracalcium aluminate, and tricalcium aluminate and tetracalcium aluminoferrate, which I have discussed earlier in previous lecture. You can go to the previous lecture to revise the further things that if in case you didn't have knowledge about all these products which are found in kiln. I also will explain later in these slides that how the temperature affects the formation of these materials, these chemical constituents. After the clinker is formed, the clinker is subjected to the fairly cool environment by convection, so that the clinker can be cooled down. When the clinker become cooled, the clinker is allowed to ground at in finer particle size, so that the cement particle size can be in the particle size between the 2 and a 50 microns. The minimum particle size would be around 2 micrometers, and the maximum must not exceed the 50 micrometer. So I have explained earlier that the OPC contain the different proportions of calcium, silica, alumina, iron, and some calcium sulfate, some concentration of a gypsum, calcium sulfate, which added for retarding the set of the cement, depending upon how long we need an open time for the cement. So we add, depending upon that situation, we add the calcium sulfate. So basic constituents are these four constituents: calcium, silica, alumina, and iron in the form of oxides. So the typical raw material we have used basically calcareous and argillaceous materials. Two-thirds of the calcareous materials, around 40 to 60% of the calcium-rich material is added alongside one-third of argillaceous material, which contain the silica, alumina, and iron content in it, so that it can be preheated and subjected to the heating in kiln, so that the clinker is formed. Afterwards, the clinker is grounded into finer product. After the clinker is cooled down, then the gypsum addition is made depending upon the requirement. These are the origin of the raw materials that we use in cement production. Basically, the four main constituents that I have explained in previous slide: the calcium, the silica, the alumina, the iron. The calcium can be obtained from the limestone, either from the marl, calcite, gypsum, marly limestone, some seashells, cement kiln dust, or chalk. Cement kiln dust also contain the calcium, because the kiln is used to fire the feed material, which contains a rich amount of a calcium. There are the residue left into the kiln, so that we can also use the cement kiln dust as a prime source of a calcium. So uh, silica silicon can be obtained from the clay, as a silica clay contains abundant amount of a silica. It can also extract from the marl, sand, shale. These are the basically geological rocks. And silicon can also be obtained from fly ash. Fly ash is a rich source of silica, which contains more than 60 to 65% or of silica, depending upon the origin from which um, the fly ash has been extracted. It varies basically. Oftenly it um, goes up to the 70% of a silica. These are the silica-rich ashes, like rice husk ash or rice hull ash. Also contain the silica around 65, and some cases it goes up to 70%. So these silica-rich ashes can be utilized as a siliceous material to be used in cement production. to be used as a raw material for cement production. Sand also contains the silica, but in crystalline form. The crystalline form is not a reactive form, so you have to make it reactive before adding into the constituent of a cement. So silica present in the sand is maybe the last option to be added. So you first explore the other options like some form of amorphous silica. So ashes contain the amorphous silica in it. So it is easy to extract the silica from the ashes um, comparatively than using the silica, crystalline silica present in the sand to be utilized in cement production. So thirdly, the aluminum or aluminum oxide Al2O3. The main source can be shale clay. Clay also contain the alumina up to 2 to 3%, 5% content. Fly ash also contain the alumina. Iron ore can be refused, can be taken as aluminous source, or some other rocks, phyllite and slate can also be used for extraction of a silica in it. And lastly, uh, iron also contain iron is basically also a constituent of one of the few constituent of a clay. Clay also contain the iron. Additionally, the iron ore you have you can extract from the iron-rich rocks. The mill scale or a shale blast furnace slag or a slag contains rich quantities of iron. These are the chemical composition, the oxides composition basically. These are the oxide composition which obtained from the X-ray fluorescence results. X-ray fluorescence is basically a technique used to quantify the oxide composition of a different constituent present in any material, like limestone, like shale, sand, ash, any fuel ash, and gypsum, etc. So in this case, we have a limestone which contains the silica content, composition of a silicon dioxide of around 2.5%, and it is rich in calcium, which is 51.92. On the other hand, the iron ore uh, have a silica content around 28% and iron content of 56, which is in majority. So it is rich in iron. Shale contain the huge amount of a silica, which is 60%, around 60%, and then alumina and or iron. It also can be taken as a iron-rich and alumina-rich source. Still, sand is highly rich in silica, which is around 90%. But I want to remind you again that this silica present in the sand is highly crystalline. It is not that much reactive than all other sources of a silica that you have before. So silica present in sand is crystalline and not desirable to be taken as a in cement production um, as it is. You just have to treat this crystalline silica so that it can become the amorphous, so that it can be desirable for the reaction, so desirable for the reactive material. So, fly ash, fuel ash contains 44% of silica and 18% of alumina. Gypsum contains the high amount of you know, a sulfate, SO3, dioxide. So, it also contains the calcium, second major constituent. So these are the XRF results. Alongside we have a LOI, loss on ignition. Limestone has a highest amount of a LOI value, which is 41.5. On the other hand, you have a gypsum of around 21.1. LOI is basically loss on ignition when your material is subjected at a higher temperature, as high as around 1700 degrees Celsius. The according to ASTM standard, the material is subjected to high temperature as high as 1700 degrees Celsius for 24 hour, and then the weight loss is recorded. So the weight loss for the pozzolanic material for a class F fly ash according to ASTM standard is around is should be within 6%. So these are the alloy values. In crushing and grinding of raw material, you what you do is you first crush the raw material into some boulders in very higher diameter particles, diameter objects like boulders. Then you crushed after crushing, you grind these materials into some homogeneous particle size. After the grinding, what you do in the grinding process there are two processes involved. First is wet process and then is dry process. Usually wet process is used when there are soft materials used. Wet process is basically a very primitive method which is used to used to reduce the particle size of a feed material or a raw material easily, so that you can have a finer particle size. This is a material used when there was not a very high technological advancement. I mean, the grinders use are of not too much hardness, so that they can grind the material in a dry form. Um, the method was formalized, wet method was formalized for grinding the hard rocks in a very effective manner. Nowadays, dry method is used as we have a very strong type of a very hard type of grinders are there, so we can gain the particle size so minute without wet without keeping it wet. So there's a comparison between the dry and wet method. In dry method, then there is very strong material type and hard material. For the wet process, we need a very soft material so that it can be grounded. Dry method, obviously, grinding is in the absence of water and in the presence of water for the wet process. So in dry process, you don't have to utilize your fuel to evaporate your water after the grinding has been carried out, after the completion of a grinding. In the wet process, on the other hand, you utilize the fuel for removing the moisture from the material. So uh, dry process, almost majority of the cement is produced in the dry process. On the other hand, the wet processes may be used in the for grinding material in manufacturing of a cement. So it's a primitive method. Wet method is a primitive method. Method is energy efficient. Low fuel is used. On the other hand, the wet method is not such energy efficient as that of dry method. So in the dry method, um, the materials are grounded in the absence of water, and the desired constituents are added and then grounded in the absence of water, to gain the desired particle size. It's around below 90 microns. In the wet process, you just pulverize the your material and then subject it to the rotary type cylinders. It contains the charge of steel balls in the presence of water. It uh, the the material is grounded into a finer particle, after which you just evaporate the your sludge to have a very fine powder. In burning of the kiln, you have a different temperature zones in it. Basically, this is a schema. This is basically a real diagram of a kiln. This is a burning source at one end of a kiln. Your material just added into the kiln from one end, then goes to you know the firing source, and the clinker is formed at that region. So this is an internal image taken in the furnace or a kiln. Uh, you can see that the semi-molten form of a you can see that the feed that we have provided in the kiln, we have added in the kiln, is in a fused form, semi-solid form. Basically, this kiln is inclined up to few degree angle, so that your charge can automatically can get to the other end without any pushing. So there are the different temperature regions in this rotary kiln uh, that we will discuss in this video. So I will discuss first the temperature zones. Um, these are the temperature zones in the kiln. And the first temperature starts that the preheating is occurred, that the preheating, basically we preheat the material so that the material can get a reactive in reactive form, and like limestone is not as much as reactive in raw form. When you preheat your material, the limestone is converted into a quicklime, which is very amorphous, very reactive to react and get the products in very short amount of time. On the other hand, you have a organaceous material containing the silica, alumina, iron in compound form. By this preheating, your silica, alumina, and iron get separated. This is basically a reaction. In limestone case, which is heated around preheating at around 1000 degrees Celsius, the it is decomposed into the quicklime and by evolving enormous amount of carbon dioxide. So the formation of a transformation of a quicklime from a lime is quite energy intensive. It involves enormous amount of energy. So in for the clay, it just separated into the some constituents, basic constituent of silica, alumina, and iron at a high temperature. For iron, around 1450 degrees Celsius, I mean in kiln, you have these products are formed, like dicalcium silicates, tricalcium silicates, tricalcium aluminates, and tetracalcium aluminoferrates are formed. So these are the temperature. This is the temperature zone for the rotary kiln. At the beginning, you have a 400 degrees Celsius of a gas temperature. Gas temperature means the gas is subjected. I mean, air temperature is 450 degrees Celsius. On the other hand, your material is just at 50 degrees Celsius. So in this temperature zone, between the 50 degrees Celsius of a material to 600 degrees Celsius, you have a dehydration. You have a dehydration of physically attached water, chemically attached water. Both physically and chemically attached water are being removed at this stage. After the 600 degrees Celsius, up to the 1350 degrees Celsius of a material temperature, you have a calcination zone. In calcination, um, basically there is in at calcination, your material become so reactive, so that it can react with the other products to make to just fused into other materials and sintered at the below them at the melting points, so that it can have a clinker formation at around 50 degrees Celsius. After the calcination, you can see that there is a clinkering zone. When the calcination happens, the material becomes so reactive, it can react with material can react with the other constituent like silica, alumina, and iron, and calcium can react with among each other to form a clinker. After the clinker is formed, you have a cooling zone. The, the cooling is occurred through the process of convection, so that your clinker can be cooled down. After the cooling, you will just ground your clinker and add some gypsum depending upon your requirement. If you do not cool your clinker and just grind and add the gypsum, you might have a chance of a fly set and a fall set in your cement. So in order to avoid that, you just add the cooling zone in your furnace. So if we talk about the chemical composition, the chemical reaction involved at the different temperature regimes, then this might be this might be the chart. In drying zone, in clinker, you have different zones. First, at temperature is raised up to the 100 degrees Celsius. Then you just have a evaporation of a physically attached water in different materials like that you are using for the clinker manufacturing. Physically attached water is evaporated. At preheating, there is three temperature zones at 100 to 300 degrees Celsius. The water is removed, the chemically attached water is removed, the water of crystallization is removed. In soil, you have a different constituent in different chemical composition. At 300 degrees Celsius, the water of hydration would be removed. uh, Between the 400 and 750 degrees Celsius, the decomposition of a shale, formation of a metakaolin is formed. For example, you have aluminosilicates hydrates. The chemically attached water present in the aluminosilicate hydrate is detached, decomposed. Then you have a product of aluminosilicates. So metakaolin, which is the chemical name of metakaolin. At temperature zone of 600 to 900 degrees Celsius in preheating zone, there would be further decomposition of a metakaolin into some alumina and silica products, oxides. After this, the calcination occurred between the temperature of a 600 and 1000 degrees Celsius. The calcination of a quicklime, very importantly, by which the lime becomes very, very reactive. The calcium carbonate converted into calcium and carbon dioxide. On the other hand, the calcium and silica alumina originated from the metakaolin, calcium from a limestone, and silica alumina came from a decomposition of metakaolin, reacted to form a silicates, which are dicalcium silicates and tricalcium, basically silicates and aluminates. After the calcination, the products become so reactive, and the when the products go up to the sintering stage, sintering temperature zone of the kiln between the 800 and 50 degrees Celsius, the belite and illite, which are basically the dicalcium silicate and tricalcium silicate respectively, are formed along with tricalcium aluminate and tetracalcium aluminoferrates. Basically, these are the chemical composition which I already mentioned in the previous lecture. How can we change the composition, these chemical compounds in your cement to have a different desired properties, to transform the cement into some different other cements depending upon your desires and requirement. So these are the example of kilns. This is what I have explained: dehydration zone, calcination, solid state reaction, clinkering zone, and the cooling zone. You must have to keep in mind that I have also already mentioned that the kiln is at inclined angle about gradient of a 3 to 4%. It has a dia of 6 meters and rotary. It's a rotary based kiln with a revolution RPM, revolution per minute of 1 to 2, which is just act as an agitator, so that your feed material can agitate and clinker can be formed. And due to this slope, the material can advance between the temperature zones so that your clinker can be formed. Raw material first enter into the kiln. Um, this image basically shows this image is a schematic of your kiln, in which the chemical compounds are formed, chemical like halide, belite, and aluminates, tricalcium and tetracalcium aluminoferrates are formed. At first, you have a preheating zone. Over here, the maximum temperature reached up to the preheating zone is around 800 degrees Celsius, at which your calcium carbonate is decomposed into calcium oxides, and with the evolution of enormous amount of a carbon dioxide. So at preheating zone, you have uh, a decomposition of a calcium carbonate. After the preheating, there is a calcination zone of for around 2 minutes, in which your free lime is basically transformed into baelite. Okay, so your free lime is converted into uh, dicalcium silicate. After the transformation, basically the calcination is just for 2 minutes. After the calcination, there's a transition zone in which your free lime is continuously in state of conversion, state of a reduction. On the other hand, your baelite production is increased at the transition zone after the calcination. This transition zone occurred for around 15 minutes. The temperature regime adopted is between the around 950 degrees Celsius and around 1350 degrees Celsius. After this temperature regime, there is a sintering occurred. The sintering of your feed material is occurred in which the formation of halite is started, and belite, you have a belite. The formation of a tricalcium aluminated tetracalcium aluminoferrite exists within the transition zone at around temperature of a 1350 degrees Celsius 13. So your sintering occurred when the halite is formed. Finally, the halite is formed. The halite is formed at a temperature regime between around 1100 to 1400 degrees Celsius. So after the sintering occurred and your clinker is formed, you allow the clinker to cool down by the natural convection method. Um, when the clinker is sufficiently cooled down, you just grind it into finely grounded particles, cement particles of a two between the particle size of a 2 and a 50 microns, and the gypsum is added at this stage. What happens is basically you just add the material. It first water of a hydration. First, the physically attached water is evaporated, which is drying. Then the preheating. In preheating stage, your water of crystallization evaporates. After the preheating, you have a precalcination in which the reactive hydrates are formed. Like you have a calcium oxide decomposition of calcium carbonate occurred at calcination, precalcination. In calcination, you have other products formed like the decomposition of aluminosilicates into the alumina and silica constituents, which afterwards go into the sintering process, at which the tricalcium silicate, dicalcium silicate, tetracalcium aluminate, and tricalcium illuminates and tetracalcium illuminates are formed at sintering stage. After the sintering, clinker is formed, then cooling is allowed for a sufficient time so that it can be grounded afterwards by the addition of a gypsum. Basically, the kiln, here is a flow diagram of all the schematic phenomena occurred. So uh, after the kiln gives you the out product of clinker. Clinker is cooled down over here. Then clinker is cooled. After the clinker cooling, it is subjected to some grinding. The clinker is added. Some gypsum is added. There is further grinding of clinker and gypsum to get a desired particle size, um, which is a particle size of a real cement. After the grinding process uh, occurred, the cement is added to the cement silos, or it goes to the cement bags, which is just forwarded for the which further forwarded to the dispatch, stores and markets. Originally, cement is stored in cement silos to prevent from moisture. If the cement catches the moisture, it can abruptly cause the hydration, and it can set, and it can be a useless material, which cannot be used for a construction if it catches a sufficient amount of moisture content. The hydration reaction will just starts. The gypsum of around 1 to 4% of a gypsum is added to delay the reaction, to delay the setting time of a cement. If the gypsum is not added, your cement would start hardening at the moment you start putting the water in it. So it gives an open time to you for completion of all the processes, all the five processes involved in concreting, which is mixing. Then second one is transporting. Third one is pouring and compacting, and fifth one is um, finishing. So uh, if the gypsum is not added into the cement, the five procedures that you carried out in the concreting of concrete cannot be successfully performed. So it's important to have an open time of a desired value. Cement is stored and distributed. Basically, it's stored in the silos at the batch plant, at the silos, so that it can easily be transported at the batch plant without being exposed to moisture. So, basically, the property of a cement depends upon two things, which is chemical composition and degree of fineness. I already have mentioned about the types of cement in previous video, that chemical composition, we can manipulate the chemical composition so that your concentration of main constituents can be stimulated, and the formation of cement can be classified based on your use. Either it's low heat cement, it's rapid hardening cement, it's sulfate resistant cement, it's not ordinary Portland cement. It depends upon the chemical composition. Secondly, you have a degree of fineness. If you make your cement particle too much fine, that it would be highly reactive. Highly reactive means it would be rapid hardening cement. It would helps to become the rapid hardening or rapid set cement by decreasing the particle sizes. If the particle size is allowed to have a very large size, then it might be a low heat cement, or it might helps to form a low heat cement. So the chemistry, the cement depends upon property of a cement, depends on both properties, that is chemical composition and degree of fineness. It is possible to manufacture different types of cement by changing the percentages of raw material. Basically, this bullet corresponds to my previous video that I have explained. You can go to the previous video. I have given a link in the description. You can follow it, and have a very and listen to the very detailed discussion um, upon the changing concentration of a different constituent to have a desired cement. So these are the chemical compounds which contains in the cement elite, which are formed in the clinker production. Basically, tricalcium silicate, which is elite, which contribute for the early hydration. Which secondly, it's belite. Its content concentration is second, which is 16 to 30%. It acts for the it contribute toward the delayed hardening of a cement. Thirdly, you have a tricalcium aluminate, which is for the early and final setting. Basically, these two products, tricalcium aluminate, tetracalcium aluminate ferrite, are used to have a initial and final set. Then you have a calcium hydroxide as a cement byproduct. This is basically a hexagonal structure, which I have showed in my previous video, which is a byproduct of a hydration reaction. This this calcium hydroxide is basically can be leached out by having different cycles of water penetration into the concrete, and it can increase the porosity of a concrete when it's subjected to the different freezing and thawing cycles, and it can degrade your concrete by leaching it out. So the byproduct Portlandite is allowed to have very low concentration in order to make your concrete very durable. So second last you have a calcium silicate hydrate, sorry, calcium sulfate dihydrate, which is gypsum. Basically gypsum is added for the delay your setting time. Lastly you have a lime, quicklime, which basically contributes toward the hydration reaction. Hydration reaction, I have explained it earlier regarding the hydration reaction. It is the reaction between the water and the cement products, in which the different products are formed, like calcium silicate hydrates are formed, attringite is formed. Mean calcium aluminosilicate hydrates are basically the attringites, and thirdly, the calcium hydroxide is formed, which is undesirable for the durability. If you discuss the hydration, you first have to define that when your cement is going to be set. When is your final initial setting and the final setting of a cement. So initial and final setting depends upon the degree of fineness of a material, and secondly you have a concentration of a tricalcium aluminate present in it. If you have a higher amount of a tricalcium aluminate, um, it would set very soon, and tetracalcium aluminate contributes toward the final set. For the setting of cement, we use the Vickert apparatus. In Vickert apparatus, you have a needle of 1 millimeter per square millimeter needle, and you just penetrate the needle into the. This is basically a Vickert apparatus, and these are the needles. If you penetrate the needle into the cement mix that you have poured in this mold, you just observe the penetration. If you have a penetration of around 5 millimeter observed from the bottom, then it would be called as initial set. For the final set, the penetration is about the 1 to 2 millimeters from the top of this mold. So initial and final set we can check by this Vickert apparatus. For the consistency, um, you use the plunger. This 10 millimeters plunger. You use this plunger for testing the consistency of a cement. You just add the water content into the cement, and determines how much penetration of this plunger into the this cement is. When it gains the 5 millimeter of penetration from bottom, then you will say that it has attained the desired consistency of a consistency. If the desired consistency is not met, you just add water content by increasing the step size of a by increasing step size of a 5 to or 10% of a water. When the at a specific water content you have a consistency means the plunger penetration is around 5 millimeters, 5 to 6 millimeters, 5 to 7 millimeters from the bottom of this plate slab, then you will say that it has gained the desired consistency. You have a 300 grams of a cement and around 30% of a water, means you have a 30% consistency. It depends upon the fineness of a cement. It depends upon the freshness of a cement, how much fresh and fine is your cement sample. If your cement sample is very fine, very reactive, then it would have a higher percentage of a consistency. So you take 90 grams of a water by adding into the 300 grams and just test the penetration of a plunger into the Vicked mold. When it gains the desired amount of a consistency, uh, it would penetrate 5 millimeters, 5 to 7 millimeters from the bottom of a Vicked mold. If you see that the cement sample in the Vicked mold uh, get get set just by adding the water, then it would might have a flash set or a fall set. Basically, these are the two sets which are caused by the reason due to the reason when the gypsum added into the clinker, into the hot clinker. Clinker is not sufficiently allowed to cool down so that the gypsum is added. Gypsum is added into the hot clinker, then you might have a flash and fall set. In a flash set, there is evolution of a heat, and the your cement become set before its setting time. In a fall set, your cement sets before the setting time without evolution of any heat or any exothermic reaction. This is a Vicked mold, Vicked apparatus. You can see that this is a cylindrical mold, 40 height with a 40 height, and this is a Vicked needle with a around 1 thickness, 1 square thickness, and the plunger has a 10 dia and 50 height basically. Uh, for the second time, you use this needle of 1 millimeter square. You note down the penetration of a needle. You note down the time at which 1 square millimeter of a needle penetrates uh, and makes penetrates 5 millimeter below the from the bottom. Those I mean this square 1 millimeter square penetration up to this value. I mean the penetration is 4 to 7 millimeter from the bottom. We can say that that time is the initial setting time. For the final setting time, your needle penetration must be 1 to 2 millimeters from the top. In case of a consistency, you must have a penetration of this plunger from the bottom up to 5 millimeters. So compressive strength of a cement is very important. It's a prime property by which we can identify the cement. It's an ordinary Portland cement, it's a rapid hardening cement, it's a low heat cement. Its compressive strength is a very prime structural property, very prime mechanical property which adds to the structural value of a concrete. So you prepare the desired mix with the desired constituents. For example, you take the 1:3 cement to sand ratio, take the water cement ratio of a 0.4, and forms the cement molds of around 76 millimeters. Then cement is compacted for the 2 meters by the vibration, and it allowed for the 3 days and 7 days curing. When you have a strength of these values 11.5 megapascal and 3.5 megapascal. So this is the strength of a cement paste. This is basically the briquette used to have a um, used to have tested the tensile strength of a cement. What you do is you just pour the concrete sample into the briquette. You have 12 briquettes in order to get the consistent results. You have a 600 gram of a cement, and you just mix this cement into the water and pour it into the 12 standard briquettes and allow it for 24 hours, and then test at 3 and 7 days. Then you just fail it in tensile intention to get the tensile strength of a cement. Usually, the tensile strength of a cement is around 10% of its compressive strength. When you have a cement consignment on site, what can you do to check the properties? These are basic properties that you can check on the site. First, you can touch the cement so that your cement should not hot. If the cement is very hot, it means the hydration reaction is already kicked in. The formation of hydration products begin. Because hydration reaction is exothermic reaction, it involves too much amount of energy, heat. So it's a high exothermic reaction. If the cement is hot, you can say that the hydration reaction is already started. So you cannot accept that cement which is hot. Secondly, you can just touch the cement and make sure that it's very smooth. Otherwise, it might have an adulteration of some stones, dust, and some sand. Make sure the cement is very smooth by touching. Uh, Thirdly, um, you can feel the cement on your hand by rubbing between your fingers. It must be smooth. So the cement is pure. You can also immerse the cement into the water. Float, it must sink because the specific gravity of a cement is much higher than the water. It must sink. The specific gravity is around 3.15. You can also check the cement by its smell. If the cement smell like earthy, it might be due to the reason that it has some clay and silt content in it as an adulteration. So you must not have accepted that type of a cement with earthy smell. Then there must not be a lumps. Cement do not contain the lumps in its original form. If it contains the lump, it means that the hydration has already been started. The formation of a hydration products. Cement lumps shows that the cement particles clock with each other to form the higher particle sizes. So presence of lumps shows that hydration is started. So lumpy cement is also be rejectable. You have a quality test of a cement. You can have a fineness test. Fineness is can be found out by a plain air permeability apparatus. According to ASTM and British standards. The on the other hand, you have other tests like sieve test of a cement, which was a part of a ESTM standard, but it has been obsoleted. So it has been replaced by the plain air permeability fineness. So you second quality test is consistency and setting time. You can get the consistency of a cement by Vicat apparatus. I have already explained the consistency and setting time. Thirdly, you can have a compressive strength of a cement. You can have a tensile strength of a cement. These are the quality tests. The fineness of a cement is basically the how the fine the cement particles are. The fineness is assessed by the measure of a permeability of a cement in Blaine permeability apparatus. The results of a Blaine permeability apparatus in the form of a centimeter square per gram or meter square per kilograms. So for the normal cement, you have a 350 meter square per kg or 2250 centimeter squares per gram for a normal cement. For a early high strength cement, you have a very high fineness, which is 500 meter square per kg. So more the higher, more the fineness of a cement, more would be the early strength due to abrupt hydration reaction. Uh, so higher fineness cement gives you the higher shrinkage. I will be discussing the shrinkage in later lectures. It's too much complicated. I will further describe the shrinkage and the types of shrinkage, its behavior, how we can reduce and fineness test, you have a Blaine air probability of apparatus. On the other hand, the fineness by the sieve method is obsoleted in ASTM, but you can use the sieve size around 200 sieve size, which is um, which is 75 micron size. uh, you can use the wet method of fineness by allowing the water, with the help of water you allow the cement particles to pass through the sieve number 200, and you just take the weight retained on sieve number 200 after having this test. Thank you so much. Thank you for watching this video. You can ask questions in the comment section for further clarification.